Okay, welcome back, class. And let's look at the last part of this example here. Uh, I think in the previous uh, video on that, we're looking at the ionization whereby you had Y. This is not for this one. So we had uh, that. Okay, so let me close let me close this door. Okay. Uh, so what we are looking at was the ionization of the substituted benzene in which there were groups attached to the para position. So the basic structure was the same, but then in one case we are putting on a methoxy group, we are putting on a methyl group. There was the unsaturated benzene, there was the chloride group, there was the cyanide group, and then there was the nitro group. Yeah. Anyway, don't worry about this graph for now. So what those figures they were giving us what we are calling the sigma value. Yeah, all those calculations, there was the Ka, and then there was the log base 10 of the Ka, and then minus log base 10 of the Ka was the pKa. So and then the pKa relative to the unsubstituted benzene, it gives us the sigma value. And then what we are seeing is that the groups which were donating electron density to the benzoic acid and therefore causing it to ionize less had a negative sigma values. And then the ones which were withdrawing electrons from the benzoic acid via either inductive or via resonance, and then causing the benzoic acid to have a more positive charge. They were causing the benzoic acid to ionize more and therefore have a positive sigma value. So the previous video was to actually generate the sigma values. So now, still the same backbone. There's the Y attached to the benzoic acid. And now we want to look at where we can look at the rate of the reaction, whereby you've got that structure now. We've now replaced the benzoic acid in that we are now not looking at the ionization. We are now looking at where it is doing other chemical reactions. Yeah, where you're doing the normal chemical reactions. What you do is this, students. If you're going to have useful data for this Hammett equation, assuming it was a complex natural product, uh, you're looking at a certain reaction with probably either it was hydrogenation, nucleophile addition, electrophilic addition, and the rest. You also need to have another reaction of the same thing in which all the part of the molecule is the same, and then the reaction center has been replaced with the benzoic acid. Excuse me, has been replaced with the benzoic acid. So that you'll now be studying the ionization, so that you're going to generate the pK as values, and that will lead to the sigma values. Yeah, yeah. So now, these are the Y values. There's the nitro group, there's the cyanide group, there's the chloride, unsubstituted benzoic acid, methyl, and then there's the methoxy group. And then now, we've now been given new data. These are the rate constants. Yeah, they're being given per mole per second. Yeah, these are the rate constant. Yeah, so you can see Uh, the one for the nitro group has got a high rate constant. The one for the cyanide, almost half of the one for the nitro group. The chloride group is small hydrogen methyl group, and then the methoxy group is very low uh, uh, rate constant. Can you see that? So what you're supposed to do will be uh, to plot such a figure. You're going to get this rate constant like for the nitro group here. You divide by you divide by what? By the one from the you divide by uh, the one from the unsubstituted benzene. So this figure you divide by this, you're going to get whatever figure. I think it will be over 100, maybe 200 and something. 32 divided by 0.269, it will be something like 200 and something. And then if I'm going to get log base 10 of that one, I'm going to get a figure something like 2.5, something like that. Huh? So that's why you're getting a figure like 2.5. So it's like 32.9 divided by 0.269, you're going to get over 200 or maybe 300 something. So log base 10 of that one will give you a figure. So this is the log base 10 of the reciprocal of this one relative to the hydrogen. Now the one for the 15.7 divided by 0.269, and then I'll get a log base 10 of that, and you're going to get a figure something like that. Yeah. So that's why you're going to get this log base 10 of the Kx, which is the rate constant, over the unsubstituted benzene, and then you take the log base 10. So you're going to plot relative to the sigma value. Okay. So if you're going to plot, these are experimental figures, and you may not get the what you may not get what a perfect straight line passing through the points. In this case, you can see like this one. There's some points here. There's some points. They're not. In fact, there may not be one which will be directly through. But this one is giving you the best straight line. But what can you see here? The gradient, which is the rho, is is uh, is a positive figure. Yeah. So this the para methoxy, this the para methyl, this the P means para. Uh, so in this case, the reason is that for a certain reaction, you can also have where you're not having just the para group, you may have the groups, like you may have a metal chloride attached to it. So just writing P and the M gives a lot of information than just doing the structure. Yeah? So this tells you that you've got the chloride group attached at the para position. You've got the cyanide group attached at the para position. You've got the nitro group attached at the para position. Here it is unsubstituted. Here you've got the methyl group attached to the para position. Here you've got the methoxy group attached to the para position. Okay. All right. So that is the gradient, and then what can you see once again? That the groups which are donating electrons to the reaction set have got a negative sigma value, and the ones which are withdrawing electrons have got a positive sigma value. So in a short while, in the next video, we're going to show what is the significance of of that uh, of that uh, raw value. Once again, you'll be surprised as to what that figure can tell you. This row can be positive, or even if it can be positive, it can be slightly positive, or it can be negative, and or it can be a very large negative. We are going to see what that raw value tells us something very critical about the mechanism, about what is happening. Yeah, it may just be simple data, but it tells us a lot of things. Well, when you've seen the sigma value, just tells us there is the this how the electron density is around the reaction center. That there are groups which are increasing the electron density. There are some which are which are decreasing electrons density. But in a short while, we'll see what the overall gradient, which is called the rho, is going to tell us about the mechanism. Yeah. Now, in this case, we are getting a linear curve. What you are going to see later, I'm just putting some curiosity in you so that you look forward to this and just, hey, I want to read more about it. What you are going to see is that okay, this is a Hammett plot, yeah. What you are going to see is that there are plots which are not, they're straight lines, but they are straight, and then after some time the gradient changes. Or it can be negative and then the gradient changes. Those plots have far more information than this, where you're just going to get a linear curve. And we look at those kind of things. So I'm just seeing how we can summarize so that we don't take time, but the Hammett plots are going to tell us a lot of things about the mechanisms of reactions. So these ones which you are looking at now, they're called the linear Hammett plots. Later we look at the nonlinear. And as I come to a pause for this session now, the nonlinear Hammett plots contain far more information than just the linear. But that one I'm going to come to later. Far more information. But once again, let me leave it at that. So I think with now the fact that we've now looked at this equation, later I'll be giving the various equations, and then we'll be giving those raw values, and then we'll see what information those raw will get. For now, we'll focus on the linear plots, and then later we'll look at the linear plots. So there's something, I believe there's something you've learned about this Hammett equation, Hammett plots. Yeah, they are purely dedicated to understanding mechanism for aromatic compounds which have got substituents at either meta or para position. Let me just repeat that one again and again. If you are going to have a group at the ortho position, or there is no, or it's not uh, there's no benzene group, that loses its rigidity. And if you're going to have a group at this position here, then that group is going to interfere with the reaction center, and therefore you're not going to get a linear plot. Yeah, you're not going to get a linear plot. What some other scientists have done, they have put those corrections when you're having groups which are either attached at the ortho position or aliphatic groups. You're going to look. I, I will just refer you to that book, the Hammett equation. It's on the website, so that you look at that thing, because this is something which can take us a week talking about this. The videos talk about the Hammett plot can go for 1 week. Maybe I can have even 7 or 8 videos, but the time will not allow, because we've got a very limited schedule. So I think for now, let me stop there. In a short while, I'm going to give uh, 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 plots showing the various Hammett plots, and then the information uh, the gradient gives about the mechanism. Yeah. So let me stop there, and then we'll proceed later. Okay. Thank you.